So a couple of announcements. So the homework for chapter 33 is due today. Forgot to change this. Work on the RLC lab. And exam 5 is on Friday. Okay. Regarding exam 5, make sure that you understand how to do the homework problems. Because you're going to see problems that are similar to the homework. Not every single one will be like it, but they'll be similar to the homework. So I really implore you to make sure you study the homework problems. Okay? Do you have any questions regarding exam 5? No questions, concerns? The exam will have 3 problems. One problem from chapter 32, one problem from chapter 33, and one problem from chapter 34. I mean, there'll be multi-part problems, and you notice that a lot of the problems in these assignments have multiple parts, so it's kind of along the same line. And you'll have some short answer stuff too. So just because it has 3 problems, it won't be as short. It won't be shorter. It's going to be essentially the same length as the other exams. But I really would like for you to make sure that you make sure you understand how to do the homework problems, the problem-solving process. Make sure you understand what, for example, what power factor means. Because I always get that question on the exam. What does that mean? Even though I covered it. Okay. All right. Since you guys don't have any questions, then I'm going to start. Today I want to talk about transformers. Then I want to do more phasor examples, and then I'll do the last chapter. Okay. And if we finish
Professor?
I'm sorry?
Oh, just a quick question for office hours, are you going to do like a review session for the exam?
Well, usually for office hours, what I do is answer questions students have. And some students will be finishing the homework. I'm not sure.
Is there a practice exam on Canvas? I haven't
Yeah,
checked yet.
so if you look at, it's not on Canvas. Remember earlier in the semester, I sent you a link to my old web page.
Oh, yeah. Okay.
And so what you want to do then is look at, I think on there it's exam 4 and the final exam. I can't remember if, sometimes when I did this class, I didn't have time to do chapter 34. So I would have, my exam 4 would be chapter 32 and 33, and then the chapter 34 problem I would put on the final exam. I didn't want to, I tried to avoid having students do like 2 or 3 exams in a row, okay? Because normally when I teach this class and I have a final, I break up the final into 2 days. And so I try to avoid having students take 3 exams on consecutive days. And so the chapter 34 problem might be on the final exam that's listed there, okay?
All right. Thank you.
Sure. Okay, so let me start by talking about transformers, and then we'll do some examples. I'm not going to spend a lot of time on transformers. Basically, a transformer has 2 coils. And usually, not always, they're linked together with an iron core. The purpose of the iron core is to increase the magnetic field and also to make sure that the flux through the primary coil goes through the secondary coil. Let me look at some of the questions in the chat real quick. Oh, okay. They're not questions, they're posts. And you hook up this side to a power supply. That produces a changing current. So this has to work. Transformers can only work with an AC power supply. Transformers work as a result of Faraday's law. Time-varying current produces a time-varying magnetic field, time-varying flux. This coil picks up that flux, changing flux, and you have an EMF here. The side that has the power supply is called a primary, and the other side is called a secondary. Of course, if I put the power supply on the right, then the right side becomes a primary and the other side becomes a secondary. Does that make sense? So either side of the transformer can be the primary or the secondary. I mean, an example of a transformer is, let me grab this, this coil. So you guys can see this coil. Okay, there's no iron core, but you have basically a circuit here and a circuit here. Okay. You actually have two sets of coils set up here. Another one, more traditional one, is this one. Oops. Two coils with the iron core. I'm going to use this for a demonstration in a little while. That one's heavy.
Are the coils coiled the same way?
You mean in the same direction?
Yeah.
That's a good question. Not actually. I actually don't know that if they're coiled in the same way or not.
I mean, I don't know if I just wonder if it would change anything if they weren't or if they were.
Well,
because like the magnetic field would go in opposite directions if they weren't, right? But it wouldn't affect each other because they're not going towards each other.
I mean, when this thing is open, let's say when this thing is open, then there won't be any current in here, right?
Yeah.
So whatever the direction of the magnetic field in here is going to affect the direction of the current in here. Isn't that true?
Yeah.
Now, when there's current going through here, that's going to affect this side.
Oh yeah. Okay.
Okay. But it's not really until I have a load here until we observed it. But that's a good question. I don't know how the relative, I'm going to assume they're the same direction.
Okay.
Okay, but I don't know. I'm not. That would be probably something I should know, but engineer would know that.
I'll look it up in the meantime.
I'm sorry?
I'll look it up in the meantime.
Okay, yeah. Thank you. Okay. So you have a changing flux through here that induces an EMF on this side, and then you can hook up a load to this thing. And they're very important. They're used to transfer energy from the power station to your home. Typically, what happens is the power station produces the energy, the power plant, and they have to deliver the energy over long distances. So that means they have to deliver the energy over a lot of wire, because wires have resistance. To reduce the resistance, the power loss is due to the resistance of the wires. What you do is you actually step up the voltage from the power station to very high values, And since energy is conserved, this term is reduced. Okay? You step up the voltage, the current decreases. These devices conserve energy. So the energy on the input side has to be equal to the energy on the output side. So if you use a transformer to make the voltage larger than the power supply, then the current decreases. If you use a transformer to reduce the voltage, then the current increases, because energy has to be conserved. So this is a schematic of a transformer. And I see your comment, Ryan, regarding the direction of the coil as a matter. Yeah, I'm just thinking about it in terms of the analysis, in terms of the induced EMF when a current's running through here. That's all I'm thinking about. But yeah, you're right. It's possible it probably doesn't matter. The analysis of the transformer is fairly complicated. Oh, okay. All right. Thanks. Thank you. So if we were to analyze this, it would require for us to do some work. And so we're going to do some simplifications, which for the most part work okay. I mean, for most practical applications, modeling it in the way we're going to model it is okay. If you're going to be designing transformers, you're probably going to have to use a better model. But if we're just trying to understand how they work, the model that we're going to use is okay. So let me show you how you would model the transformer circuit. The first picture shows you the transformer. The transformer itself, the coils, have self-inductance. The coils have resistance. The primary and the second coil are linked together through mutual inductance. So you can see the analysis would be somewhat complicated. We would not use phasor diagrams for this. Okay? But we're going to make some simplifying assumptions so we can analyze this and get an understanding of how they work. And if we want to get a better model of it, then we would have to use these circuits and analyze them. One of the other complications is the fact that if you use an iron core, iron has a complicated behavior, and that makes the analysis much more difficult. Another complication you have is because you have a changing flux through this coil, then the iron, which is a conductor, is going to have a current going through it. And of course, this is going to have resistance. And so you're going to have I squared R losses, eddy current losses, within the core. And so you're not going to get all the energy transferred from the primary to the secondary because of this core. And what a lot of folks do when they design transformer, they laminate the transformer core to increase the resistance and reduce losses. You can also make a transformer that's air core, meaning it's just the only way these two are linked to each other is through air, not through an iron core. It's actually not that hard to design a transformer that's over 90% efficient in transferring energy. So I want to make some simplifying assumptions so we can analyze a transformer. We're going to assume that the inductance on the primary side is much, much greater than the resistance. We're going to ignore any resistive losses in the primary because of any resistance we have. And we're going to ignore any eddy current losses as a result of the iron core. The purpose of this iron core is to make sure the number of flux lines that go through this coil match those going through that core. Okay. Because the resistance on this side is essentially 0, then the power factor is 0. And P average on the primary side is essentially 0. So no power loss. On the secondary side, we're going to assume that for whatever load we have here, the resistance of the load is much, much less than the inductance of the secondary. It's purely inductive. And this is an ideal transformer. So, when there's no load that exists on this side, it turns out that there's very little current going through here. The current that's going in here is called a magnetization current. It's a small current. But that small current is going to produce a large magnetic flux in the core. And in fact, if you have a changing flux on this end, your d phi of B over dt is going to be your d phi dp on this side is going to be equal to the power supply, and then on the opposite side, we have that. This is the induced EMF, and we'll call this delta V1. We'll call this delta V2, and I'm ignoring the minus signs. These two are common to each other because we're saying that the number of field lines going through here equals the number going through there. If we take a ratio, that's how the voltage is linked together between the primary and the secondary. Now, on the primary side, this voltage is fixed by the power supply. On the secondary side, it's not. There's no power supply there.
Is that E the epsilon, or is that the E with the squiggle on the bottom?
E with the squiggle.
Okay.
Because a lot of times it's used to represent EMF. But I'll write them as delta V1 and delta V2, okay?
Okay.
And so the transformer, the ideal transformer, goes by this equation. It's very simple. The ratio of the voltages is equal to the ratio of the number of turns. Now, if N2 is greater than N1, then delta V2 is greater than delta V1. And we say that this is a step-up transformer. If N2 is less than N1, then delta V2 is less than delta V1. We call that a step-down transformer. So when energy is delivered from the power station to your house, the voltage is stepped up with transformers, and you have these high voltage lines. You can see them in Roseville. If you go by the fountains in Roseville, you'll see these high voltage wires. Okay, those are That's coming from a power station. Those are very high voltages. Then when you get to a substation near a home, the voltages gets stepped down, and then they get stepped down again as they come, the lines get into your neighborhood and into your home.
I remember seeing a picture of that.
I'm sorry?
Oh, I remember seeing a picture of that in the book where it showed from the power plant to the power lines to the house. And it said step up, step down, and such.
Yeah, so both are used. All right, both are used in delivering energy to your home. But the real analysis is more complicated than this, right? I mean, it's like the analysis we're doing here is kind of like when we do projectile motion, we're doing air resistance. Okay. Now, I want to add to that because we're assuming no energy losses here, no energy losses here. And if there were a load here, then we'd have just the energy loss due to the resistance. If there was current going through here, we would say delta V1I1 equals delta V2 I2. If I had a load here and I had current running through here, the input power has to be equal to output power. That means that delta V1 over delta V2 equals I2 over I1. That must be true also. Now, this is an interesting effect. When I have it set up like this, I have very little current going through here. The current is called the magnetization current. When I put a load here, whatever type of load it is, whether it's inductive or resistive, I will now have a current I2 in here. But that I2 varies with time, which means I have a magnetic field that varies with time. That's going to affect this side, because now this current is going to cause a changing flux too. But the problem with this side is this power supply sets the voltage, fixes the voltage drop across the primary. Even though there's an induced EMF because of the changing flux due to I2. And so what happens is, to oppose that changing flux, the current in here increases. So the current here ends up being whatever is induced plus the magnetization current. And the induced current is way larger than the magnetization current. So I'm going to demonstrate that to you. I'm going to make sure my power supply is plugged in first. And this demonstration, if you go to there's a YouTube website called Sierra College Physics and Engineering, and Tyler made a demo of this last semester. Okay, so let me show you the setup. Let me get rid of the PowerPoint slide. So here's my transformer. And this is the primary side. I have just a resistor to limit the current. I'm going to have this. So this, by the way, on the primary side, I have a coil with 250 turns. And on the secondary side, I have a coil with 500 turns. So I'm going to step up the voltage by a factor of 2. Originally, when I set this up, this thing had 20,000 turns, and that kind of scared me because I would go from 70 volts to 7,000 volts. I didn't want to do that. And so I hear a light bulb. I'm sorry, this is I'm sorry, I did that backwards. This is the primary side, this is the secondary side. 500 turns, 250, so actually cutting it in half. So I'm setting it to about 70 volts. This light bulb is not on. This light bulb is on the primary side, sorry. Okay? And then I'm running a current through the secondary because, okay? So I'm going to flip the switch, and this is the primary side, because right now there's nothing. I'm going to flip a switch so I run current through the secondary, and then on the primary, now all of a sudden the light goes on. Let me turn it off. This is on the primary side. I run current through the secondary side, and the light bulb goes on. Okay? So the current that's initially running through the primary is small. It's not until I run current through the secondary that this light bulb goes on. Okay, let me turn that off before I get shocked. Questions on that? Okay. So one of the things too is that this current and this current are going to be 180 degrees out of phase with each other. Okay? Because of Lenz's law. Okay, because of Lenz's law, they have to be 180 degrees out of phase with each other. Now, suppose we have a load on the secondary side. Suppose we have some sort of load. Let's make it some resistive load. What is the equivalent resistance of that on the primary side? What do if I'm on the primary side, what is the equivalent resistance on this side? Let's start with that equation. Okay? I want the equivalent resistance of the primary side when I have a load on the secondary side. And we'll start with this equation. So I2 is just going to be delta V2 over our load. I1 is going to be what? It's going to be, if I solve this for I1, it's going to be delta V2 over delta V1 and this is going to be equal to delta V1 over R equivalent. I want to solve for R equivalent.
Hey, Professor, can I ask a quick question?
Yeah.
So whenever the term is used like a load, that's just referring to some voltage drop across like an element of a circuit, like a resistor or a capacitor.
Yeah, load is something that's taking the energy out of the system, basically.
Oh, okay.
Something that's
Okay, cool.
dissipating, yeah, like a resistor.
Okay. Thank you.
So that way you're drawing current. Because when you have an open circuit, you're not drawing any current. When you put a load there, you're drawing current and it's using up the energy.
Okay, that makes sense. Thank you.
So I'm going to solve for R equivalent. And let's see, I'm going to get RL. And so R equivalent then, so delta V1 over delta V2 is N1 over N2. So that's the equivalent resistance on the primary side. So one of the things we learned early in the semester, and I kind of ignored the problem in this chapter, is if you have, I don't know if you remember we did the problem with the power supply, the internal resistor, and its resistance. And to get the maximum energy transfer to this thing, these two resistances had to be equal. And so if you put on the primary side a resistance equal to that, you're going to get a maximum energy transfer to the load. When people use speakers, a lot of times what they do is they put a transformer between the amplifier and the speaker to match impedances so you get maximum energy transfer. Now that's another application of transformers. There's different types of transformers. There's some transformers you can isolate grounds. Okay, there's different applications of transformers. You may want to isolate your ground from the ground in your home just because you might be working with something somewhat dangerous that could affect what's in your home. And if you work in an accelerator lab, for example, and you're working on a power supply that runs at 30,000 volts, you want to isolate the ground from that system with the ground of the building. That's what I used to do in research. I would work on an accelerator. The accelerator would have its own ground isolated from the ground of the building because the accelerator was running at 30,000 volts. In fact, its ground was at 30,000 volts. Okay. The whole accelerator was floating at 30,000 volts. Okay. So really this is it regarding transformers. I don't have a lot to say about them because in this course, a discussion of the analysis of transformers would probably take a couple of lectures. And if you're interested in that, you would probably, if you were a power engineer, electrical power engineer or electrical engineer, you would learn more about the details of how the transformer works. The analysis is somewhat complicated. It's doable. I mean, if once you learn the materials from Engineering 17, are any of you taking Engineering 17 next semester?
I'm pretty sure I am.
Yeah, so if you learn the techniques in that class, that circuit that I showed you is pretty easy to analyze. A lot of algebra, but you can do it. Okay, so that's it for the chapter. What I want to do is a couple more examples on phasors. One of them is a hard problem. Actually, they're both a little more challenging. And my hope is that it helps you to better understand phasors. And really what my hope is that you understand how to create the phasor diagram to solve a circuit. And the first example I'm going to do is related to, well, essentially is, yeah, one of your homework problems. So let me draw the circuit. And no, don't worry, I'm not going to put an exam like this, a problem like this one on the exam, okay? Because this one would take time. So this would be, when I said that the exam problems would be like the homework problems, this one would be an exception. Okay, so let's say we have power supply, a capacitor, a resistor, and an inductor. So how do we analyze that circuit? Before I start drawing the phasor diagram, I have to draw the phasor diagram to really understand the circuit, to really solve it. I have to draw a good phasor diagram. But what do I know? I know that the voltage across the inductor has to be equal to the voltage across the resistor because they're in parallel. In fact, I can also say this. These are the time, right? This is the time-dependent part. This is just the amplitudes. Because of Kirchhoff's current rule, I can also say that the current through the capacitor is equal to the current through the resistor plus the current through the inductor. Isn't that true? I also know that the voltage across the inductor leads current by 90 degrees. And I also know that the voltage across the resistor is in phase with its current. In fact, I also know that the voltage drop across the capacitor lags the current by 90 degrees. Okay, so I know that. So what do I do? Well, let me start drawing my phasor diagram. I'm going to draw my weird coordinate system. It's harder to see. That's okay if it's hard to see. As long as you can see the phasors. So I guess the first question is, how do I start? I know that this current is equal to this one plus this one. Since these two voltages are the same, since the voltage across the inductor equals the voltage across the resistor, and the current lags the voltage by 90 degrees, here the current's in phase, that means that these two currents have to be 90 degrees apart. So the two currents That must be true. So when I draw my phasor diagram, these are perpendicular to each other, and their sum has to equal to I sub c, because I sub c is the total current. That makes sense?
Yeah.
So let me start by drawing I sub c then. Let me draw that I sub c. Now, the sum of these two, which are perpendicular to each other, has to equal to this. So this has to form a right triangle. So how do we draw that?
We also said that the voltage across the capacitor lags by 90 degrees.
Yeah, so I could write the voltage across the capacitor like this, right? Right?
Yeah.
So I can draw that in. Okay, that's fine. What about the voltage across this guy and this guy? Well, they're the same. I got to draw this right because, see, if I draw,
Well,
I can't do this, watch. If this is I sub L, and this is I sub R, and then the voltage across the resistor is this, then I can't do this because now my current leads my voltage. The current across the inductor leads the voltage. So I can't draw that.
could you switch them?
I can switch them, and so that's what I'm going to do. I'm going to say this is I sub R, and darn, I don't have enough colors. Purple, okay.
You could use black.
Yeah, I want to use black for the sum, I guess. This is I sub L. And then I can write this is V sub R or V sub L. So when I draw this, I can see that this lags behind that, which makes sense. So this is the voltage across, the big blue one is the voltage across either the inductor or the resistor. This is the voltage across the capacitor. So this plus this has to be equal to the power supply voltage. And so I'm adding vectors. Let me slide this over here to add them. Because when you add vectors, you can slide them anywhere, right? And then this is the power supply voltage. Let's label some angles. Let's call this beta. Let's call this phi, because this phi is the angle, the phase angle between the power supply voltage and the current through the power supply, because I sub c is the same as the current through the power supply. That's my phasor diagram. So what can I figure out? Well, what's beta? I know that tangent of beta because this angle is 90 degrees is I sub L over I sub R. And that means that this is going to be V sub L over X sub L divided by V sub R over R. Well, these two are the same. So if you know R, L, and omega, you know what beta is already. Okay, if you know your resistor value, you know L and you know omega, you know what beta is. That's nice. Now, this length, this horizontal component, if you look at this horizontal component, it can be written two ways. It can be written as V sub S cosine of phi, or V sub R cosine beta. Isn't that true? Isn't it true that this length is equal to this length minus that length? Now, since this thing goes straight down, this is a 90-degree angle, this has got to be 90 minus phi. This has got to be 90 minus beta. Can I write it? Can I solve for V sub S? If I know this and I know this, can I solve for this? Can I find a relationship between them? The answer is yes. Because if I know this angle and I know these two, I can solve for this from the law of cosines. If I use the law of cosines, this is going to be equal to this squared plus this squared minus 2 but this is I sub R times R. This is I sub C times X sub C. But I know how these two are related from that. I know that I sub R is I sub C cosine beta. So I can substitute this over there. Remember, I sub C is the total current. If I substitute this here and this there, then I have the voltage in terms of the total current times something else. That's the impedance. So I can write V sub S is equal to I sub C times a whole bunch of stuff. And that's the impedance of the circuit. Okay, all I got to do is make this substitution, and then all I got to do is factor out the I sub c, and I have my impedance for the circuit. Okay, although I got to take the square root of both sides, but I'll give you the impedance of the circuit. Questions on that? And you really have enough now to be able to solve that problem in the homework, because the rest of it is just algebra. Once you have that picture and you've written out all the equations from geometry, you can solve it. It's a little tedious algebraically. I will say this: when you take engineering 17, you won't be drawing the phasor diagram. You'll be using this concept called phasors, which is basically writing your voltages in terms of a real part and an imaginary part. Okay, what I've drawn here is actually I'm focusing on everything on the horizontal axis. Everything on the vertical axis is the imaginary part of the circuit. Everything on the vertical axis, the reactive part, is related to the reactive part of the circuit in terms of the reactance. But what you'll do is you'll write them in a different way. You'll do it more mathematically, and it's much easier to solve. That circuit is very easy to solve using the methods you learn in engineering 17. And as the circuit gets more complicated, this method becomes more cumbersome. And you're going to use a method that's basically just like adding vectors, the component method. Questions on this? Okay, let me do one more example. This one's in your note. This is one I rarely get a chance to do. Go back. This is a problem with a real inductor. And it's completely solved in your notes. Okay. The wrong way, sorry. So let me make this picture bigger. It might be hard to see on the screen. So I have a circuit with just a resistor and an inductor. The inductor is a real one, meaning that it does have resistance. And so we're given some values in this circuit, and we want to solve it. So just give me a chance to erase the board. And we'll go through this one. So let me draw the circuit. The dotted line represents the real inductor. Okay, this is R. We're given R. Big R is 50 ohms. Okay. We don't know L. We know this is 110 volts RMS. Now, we're also given the voltage drops. The voltage drop across the resistor is 50 volts. the voltage drop across my real inductor is 90 volts. I want to know what L is. I want to know what little r is. And the power loss in the inductor. Well, these are in series, so whatever current is going through this resistor has got to be the current through the inductor. So isn't it true that the current is 50 volts over 50 ohms? It's 1 amp. So far, so good. But now I need to draw my phasor diagram for this problem. Now let's think about it. Let's draw the current. They're in series, so let's draw the current. And the voltage through both resistors, we'll write it like this. Whatever current is in here, I mean, whatever voltage is across this, got to be in phase with the current. Because it's in series with everything else. Now the inductor, the pure inductor, a pure inductor, its voltage drop would be 90 degrees ahead. Make it bigger. I'll put V pure for pure inductance, okay? But this is not 90 volts though. That's the voltage across this, not this. The voltage across this is this guy plus that guy, but the voltage across the little resistor is in parallel with this current. This is the 90 volts. Okay? And then the rest from here to here is V sub big R.
So V sub pure is the same as V sub L, right?
Yes, I mean the pure
Okay.
inductance, yes.
Yeah. Okay.